Okay. Okay. So, Lucia, if you want, you can show your presentation now. Okay. So we see it perfectly. Thank you. Okay, so welcome everybody to this new session of the Severo Seminar course. Today we're pleased to have with us Professor Lucía Barbu. Lucía Barbu is a Serra Hunter lecturer at the Technical University of Catalonia and also an affiliated scientist at CIMNE, where she's leading the fatigue unit. She has obtained her PhD in structural analysis in 2016 at UPC and has continued to pursue research in computational solid mechanics in the following years, with a special emphasis on the constitutive modeling of fatigue processes for steel and composite materials, as well as on developing computational methods for the nonlinear analysis of pre-stressed structures. Today, Lucia is going to talk us about numerical framework for fatigue simulation that she has been developing. Lucia, when you wish. I think you're muted.
Yes, definitely. Now you can hear me well, I hope.
Yeah, perfect.
Great. Okay. Well, hello everybody. Thank you very much for the presentation, Ignacio. Let me just say that it's a pleasure for me to be with you today. Unfortunately, I can't be with you in person because I am still COVID positive. But well, it's still an opportunity for us to share with you, for our research group to share with you our knowledge on fatigue, even if in this virtual format. I apologize also if I have any coughing or sore throat. Still, I have some issues with this, so sorry for the noise. Okay. Okay. Now, today I want to share with you the work we've been doing in the past years regarding the numerical simulation of fatigue processes in our group. And when I say our group, you know me, Ignacio has just presented me. I'm Lucia Barbu. Together, I work with Alejandro Cornejo, who is a postdoc researcher in our fatigue unit. Then we have Sergio Jimenez, who is a PhD candidate who is just finishing writing his thesis. He's finishing his PhD, and he will be defending his thesis hopefully in October this year. Then we have some new PhD students who are working with us. We are very happy to have them. Luis Antonio Gonçalves has joined us from Brazil, working on fatigue and the influence of manufacturing processes on the fatigue behavior of metals. Then we have Ali Reza, who is joining us from Iran, and he's working on composites under fatigue and also a formulation for delamination. And we have Barbara Alcaide also with us. She's a naval engineer, studied here in Barcelona, and she's working on the composite behavior of the fatigue behavior of composite materials, helping us with a specific application for the automotive industry. Now, all of us are very lucky to have collaborated and received very good advice from Professor Sergio Oyer, who is a former full professor of UPC, of the Polytechnic University of Catalonia, and also CIMNE. Professor Oyer has retired in the past years. He's working in Argentina now, but he's collaborating with us quite regularly on whatever issue may arise. Okay, now, my objective for today is to share with you the approach proposed from CIMNE for the analysis of fatigue processes. Today I will focus on metals, and I will just touch very briefly on composites because there's not enough time to speak about everything. And I want to begin my presentation with a general overview of fatigue and some general issues, some general concepts which are relevant for fatigue that's important for all of us to know beforehand. Then I want to speak about the formulation we've developed at CIMNE for different types of fatigue, high cycle, ultra-low cycle, and I will center my presentation on low cycle fatigue, which is the challenge nowadays, at least for us. And afterwards, I want to speak about some future work that we're planning on developing. Basically, what about the simulation of manufacturing processes, which have a significant influence on the fatigue behavior? What about thermal fatigue, another hot topic? And I want to close with a short comment on composites. Okay, now, when we are speaking about fatigue, what are we referring to? Now, I hope all of you know, and if not, this is a good opportunity for you to find out. that fatigue is associated with cyclic loading. And this is a type of loading which induces inside the material, when fatigue is recorded, a permanent, progressive, and localized structural change. Okay, so we have alteration in the material properties due to this continuous application of the cyclic loading. And the most widely known instrument that is generally used in the fatigue domain are the Volar curve, or the stress number of cycle curves. You can see an example here in the picture that you have on the screen. And this is a good way of showing you the different types of fatigue that can be found are actually represented on this SN curve. For instance, in this right part of the curve, we can see the behavior of high cycle fatigue. High cycle fatigue is characterized by quite large fatigue lives in the order of millions of cycles, hundreds of thousands of cycles. Primarily, we have elastic deformation inside the material, and the stress levels are quite low, below the yield threshold. Okay? The fracture associated with high cycle fatigue is brittle, and I want to say that this is what was initially understood as fatigue. In the 1960s, when fatigue became an issue worldwide, this is what was conventionally associated to fatigue, this concept of high cycle fatigue. Okay? Now, later on, there was also another type of fatigue developed or understood in literature, which is ultra-low cycle fatigue, which is the other end of the spectrum. Here we have quite low fatigue lives in the order of dozens of cycles, maybe hundreds of cycles. We are dealing with a behavior which is completely different from high cycle fatigue. We have advanced plastic deformation, and the stress level is considerably greater than the yield limit, and the fracture in this case is very ductile. Now, in the middle, we have this gray shady area, which I will call low cycle fatigue. The lives are in between the two poles that I mentioned. So let's say about thousands of cycles, hundreds of thousands of cycles, tens of thousands of cycles. We can have plastic deformation, of course, at several different levels. And the stress levels are close to the yield limit when we are closer to the high cycle domain, and they progressively increase as we get closer to the ultra-low cycle fatigue domain. Okay, now let's see a little bit what's the characteristic state of the art. Let's see what the industry does, what the researchers do in each of these types of fatigue. Now, regarding the ultra-low cycle fatigue, I would say this is somehow the newest fatigue area, which is studied in literature. And here is the area where mostly we have research-based work. So we have a lot of models developed ever since 2003, 2004, 1995. In our group, Professor Xavier Martinez has also proposed a model specifically developed for ultra-low cycle fatigue, which I will explain later on its particularities. And this is, I would say, the area which is further away from the industry at this specific model. Now, low cycle fatigue is somewhat more standard or more taken into account by the industry, because we have some standard rules which are implemented in different fatigue softwares. For instance, the Coffin-Manson rule, which is, I believe, the most widely used, the Baskin rule, the Morrow rules. Here is an area where normally you find damage and plasticity models, sometimes joined together. And most of the models which are developed in this area are based on two base model, I would say, which is Chavosh model and Lemaitre Chavosh, developed in 1988 and in 1990. Now, there are a lot of researchers who are working in this area, but a lot of the models which are proposed nowadays are generally extensions, are based on these two models. Now, regarding the high cycle fatigue domain, this is the domain which is closer to the industry, I would say, because every car manufacturer, part manufacturer is worried about fatigue. They have they're paying licenses for specific fatigue developed plugins, such as ENCODE, for instance, which is very famous and very well documented, FemFat, FESafe, Fatigue Plus. There are a lot of softwares out there for high cycle fatigue domain. And generally what you will find in this area is a preponderance of damage models, majority of damage models, They are based on SN curve, on the Volar curves. And in the case that where we have a combination of cyclic loading, you will find that most people and most softwares also use the minor rule, which is a linear damage accumulation rule, summing up the damage due to each different type of cyclic loading. Also, there is another family of models which has been proposed in the last years. I would say starting from 2014, 2015, which is the critical plane approach, which has its own particularities. It's interesting for you to check it out if you're curious about this. However, this is not the approach that we are using at Sim. Now, I would say as a general overview, what's important for us to note here, that there's no universally approved constitutive model, okay? And conventional models here require regular cycles to predict fatigue life. And another conclusion that we can draw after reading a lot of literature from the different types of fatigue is that no model can describe the three types of fatigue together or transitions in between one type and the other using the same thermodynamical framework. Now, just to make our talk smoother later on, I want to establish a base for specific terms that you will be hearing throughout my talk, okay? Now, when we are dealing with cyclic loading, we have a cyclic force or cyclic displacement, which is applied on a specific geometry. And this cyclic load, force or displacement, induces inside our geometry a cyclic stress state at each specific, for instance, finite element or specific integration point of a finite element. Okay, so we have a stress state, cyclic, at each integration point, and we can compute based on this specific stress state a reversion factor, stress ratio it's called, this R factor, which is the ratio between the minimum level of stress recorded at that integration point with the maximum level of stress recorded at the same integration point. So throughout our geometry, all of the integration points inside all of the finite elements, they have their own specific stress ratio, okay? Of course, we can compute what is the maximum level of stress inside whole geometry, what is the maximum stress ratio inside our geometry, etc. But just to explain what is this stress ratio. Then, what's also important for fatigue formulations, especially in the high cycle fatigue domain, is what's this maximum level of stress recorded either at each integration point or whole geometry. Also, the mean stress, the medium level of stress recorded, because here you can have different types of cyclic loading. For instance, completely oscillating, where you have zero mean stress, or you can have tensile mean stress, etc. Also, you can record the amplitude of the cyclic loading and the amplitude of the stress state induced by the cyclic loading. I want to be precise here. Okay, now all of these cyclic loadings applied on specific components, they induce a change in the material properties. And these changes, they are recorded for a specific geometry by means of the stress number of cycles Volar curves. What's important for me to explain to you is that there is no single stress number of cycle curve. There is a whole family of Volar curves, which each specific stress ratio, for instance, has associated a specific Volar curve. So we can somehow understand the concept of SN curves as a smooth surface, okay, which vary with the reversion factor. An important concept also to understand is that the Volar curves, they tend, as we accumulate the number of cycles for very high fatigue lives, millions of cycles, they tend to an asymptotic behavior for most metallic materials, not so for aluminum alloys, okay? But most materials, most metals exhibit this type of asymptotic behavior with large lives, millions of number of cycles. And this, the stress level associated to this asymptotic line, this is the endurance limit, or what is very commonly known as the fatigue limit. And this is a limit that's very important for the industry, specifically when they design for high cycle fatigue loading. Because if you manage to maintain the stress state inside your specific component that you are interested in developing below this endurance limit, then you have no fatigue behavior. You will have no alteration of material properties as you apply the cyclic loading. This is a very easy way to design, I would say. And this is basically the main design practice in the past 20 years or so. However, throughout globally, I would say, transversally in all different industries, we are in a process of greening out our manufacturing processes, the way we design components, the way we handle mechanical parts, etc. And in this sense, there is a large trend regarding lightweighting. So as we reduce, for instance, the weight, as we reduce the thickness of different mechanical parts, then we start to have higher stress levels. And this design, which keeps the stress level below the elastic limit, is no longer feasible in many cases. This is why all the different formulations for high cycle fatigue developed throughout in the research world, they start to have a lot of importance, and the industry is starting to be very, very interested about this. Okay, now regarding the failure due to fatigue, let's just say that there is a characteristic pattern when you see a fatigue failure surface. Basically, you have fatigue initiates in an origin, which is generally found close to a defect in the internal structure of the material. It can be a large pore, it can be an inclusion, etc. Then you have this area where you have a propagation of the crack, which has initiated that defect, where you can see this clamshell pattern. And in the end, when we've propagated throughout the cross section until you reduce this cross section to such a small level that you can no longer bear the load, then you have a final fracture which is quite brittle. Now, another concept that is important to establish at the beginning. When we are dealing with cyclic loads, I don't want you to think that we always have regular cyclic loading, because this is not the case. This is the simplest case possible. But a lot of the mechanical components that industry use these days, they are dealing with either with sequences of regular cyclic loads or combinations of different cyclic loads. And here, for instance, you need a rule which helps you sum the effects, the damage effects, for instance, of each one of these blocks. The most widely used is the minor rule with linear damage accumulation. But also you can be dealing with irregular cyclic loading. And in these cases, you need to take into account that you have to use a cycle counting technique, such as rainflow, I would say is the most famous one. And after you divide this irregular cyclic load into cycles with similar characteristics, you group them and you apply them into a specific order, then you can apply the minor rule. Okay, now let's go to the similar formulation for high cycle fatigue. Now, this is not a new formulation. We've developed it a long time ago, I would say. During my PhD, actually, I worked on this formulation also. And let's just say that it's based on a very simple damage model. Okay, you can see the constitutive over there. But this continuum damage model by itself is not sensitive to fatigue. You can apply millions of cycles. You will have no change in the material properties. And if you have elastic deformation, you will be permanently in elastic behavior. But we know this is not what happens in fatigue. So we need to change the model somehow. So we have decided to affect the damage threshold condition by a residual strength function, which is a function which progressively lowers the strength of the material as you apply cycles based on a specific parameters, such as, of course, the number of cycles applied, the reversion factor of each specific stress state at each specific integration point, and also the maximum level of stress at each integration. So a little bit more detail about this reduction function. Basically, it's an irreversible factor. You cannot go back. You cannot recuperate it. Well, go back. It starts at the beginning of a simulation when you have a virgin material with a reduction coefficient of 1. And as you advance and you apply a number of cycles, then you progressively lower this coefficient. Basically, the effect it has when you include it inside this damage threshold condition is it either amplifies the current stress state until you reach the threshold and you go into the nonlinear domain, or you can see it absolutely equivalent to reducing the maximum admissible stress inside your material. And the expression of this reduction function is related 100% with the Volar curves, with the stress number of cycle curves. What do I mean related? I mean, it depends on the same material parameters that you have to calibrate. So if we take a look, for instance, for a typical SN curve, okay, we normalize it with the maximum tensile strength. And we see that for a specific level of maximum loading, what the SN curve is going to give us is what is the maximum fatigue life that the material can withstand at that stress level. Okay, when we add into this equation also the fatigue reduction function, what we are doing is that we are obliging it to respect two different conditions. It should begin also with in a level of 1, which would be the static tensile strength of the material. And this function is necessarily having to pass through this intersection point over here, which tells us that we have reduced, we have lowered the strength of the material sufficiently that we are crossing the level of maximum stress, and this is when we are breaking our specimen at that specific material point. After that, the evolution that it has in between these 2 points, this will depend on the material parameters that we will have to calibrate. Now, the expressions of these two functions, they are here, they're quite complicated. Just bear in mind that they depend on these specific material parameters. The formulation is a little bit more complex. Here you can see all the equations. Also, you can consult our publications, and I will pass them to you if you're interested. But let's see how do we derive these material properties. I have to say that all of the models in the fatigue world have this problem that we have to calibrate material parameters. There is nobody who is free of this issue. So some time ago, we decided to help ourselves to have an easier life. And we decided to develop an automatic calibration algorithm for these parameters, so we don't spend half of our life tuning these parameters and the other one, etc. So in this sense, the automatic calibration that we are using right now is based on the function fit from MATLAB. It has greatly simplified our life because in just a matter of minutes, you already have all the material parameters that you need. You can see here, for instance, an example of calibration for the complex phase 800 steel, which is used in the automotive industry. And the material parameters derived from this automatic calibration processes you can see over here. Just to mention that this is a material which is manufactured by ArcelorMittal, and the material was tested inside the AutoCAD facilities. This is why we have their partners with us in the Fatigue for Life project. This is why we have these experimental data available. Now, some other examples of calibration for other materials, for instance, for the UC-Bor 1500, which is another material used in the automotive industry, or the 22 manganese B5, another material used in the automotive industry. Both materials are produced by ArcelorMittal, and also they have been tested by them. And just to finish this part, I want to stress that we are not working with discrete, with isolated SN curves. Okay, when we are calibrating these materials and we are calibrating specific curves for specific reversion factors to experimental points, what we are actually doing is we are configuring this whole surface, okay, of the SN curve. So, for instance, if in a numerical simulation, in finite element simulation, you start to have damage due to fatigue, for instance, what will happen is that you will have right away a stress redistribution outside of the area where you have damage. This means that the stress state will be altered at those specific integration points inside those specific finite elements. This means that even if you begin with a stress ratio, for instance, of -1 or 0.1, you will have points that throughout the nonlinear process will change, will go away from that SN curve, which is specific for -1. If you have a model which only takes into account discrete SN curves, you are going to be in an indetermination if you are going away from that specific SN curve. This is why it's important to have a continuous, well-defined surface of stress number of cycles curve. Okay, and this is what we are doing inside our formulation. Here you can also see, for instance, what the surface, the reduction surface looks like when you intersect it with the SN surface for a specific level of maximum stress of 700 megapascals. Okay, now an important thing for us, and this I didn't mention in the state of the art. Just let me say that when you are using the minor rule, the linear damage accumulation rule, although it is very widely used because it's very easy to use and it's a useful tool for the industry, the minor rule is not always correct. It has been invalidated for several different types of materials. Why? Because the minor rule assumes that each cycle of loading has exactly the same degradation level, even if it's the first cycle of loading, even if it's the 100,000th cycle of loading. And this is not correct. It was demonstrated that the sequence in which different cyclic loadings are applied, so if you're in cycle 1, or if you are in cycle 2000, or if you're in cycle 200,000, the degradation level is not the same. It can be different. So it's important to have models that are able to account for the load sequence effect and for the damage accumulation effect. And in this sense, we have been working together with our colleagues at Eurecat, which is the Catalan Research Center, on designing an experimental campaign that can help us demonstrate that our model is perfectly capable of accounting for this load sequence effect. Now, when you start to do this type of analysis, an important thing that you have to make sure is that you are quantifying correctly the change in the material properties for each different block or each different cyclic loading. For instance, here we have in the first image, we have a determined blue cyclic loading with a level of maximum stress, which is S max 1. And after that, we apply cyclic loading, which has a lower level of maximum stress, although we maintain the same reversion factor. In the image on the right, we are switching the ordering between these two. And in order to be able to account properly for what would be the fatigue life resulting from these two different load combinations, you need to make sure that you are quantifying correctly what's the change in the material properties for the first type of loading, for the second type of loading, etc. In order to do this, as I say, we've been working with Eurecat, and we've done a study on the complex phase 800 steel. This is the shape of the specimen which they tested, and this is the finite element model that we've used in our numerical simulation. And what we wanted to see is if you apply a determined number of cycles, which we decided together it's going to be 31,000 cycles, and then you break the sample monotonically, we were interested in finding out if the maximum level of stress attained by that specific specimen after having applied 31,000 cycles was the same as in the beginning, the same as for the virgin material or not. What they saw experimentally, was that there was a reduction inside the maximum stress achieved inside the specimen of about 2%, 2.8%. Basically, the maximum level of stress went down from 885 megapascals to about 865, let's say, as an average. Okay, so we started to do the same numerical simulation, where we applied the number of cycles, and then we broke the sample monotonically, and we took a look at what was the reduction factor after 31,000 cycles, and you can see here what are the areas which are which have reduced strength due to having applied these 31,000 cycles. Okay, and then we looked at what was the level of maximum stress that we obtained in the numerical simulation following this exact same load history, let's say. We found that we had a really good agreement in this sense. So now we are working on designing the load sequence campaign experimentally. They are doing experiments, and then we have to, when we receive the results, we have to also reproduce them. Okay, now something else that's very interesting for the high cycle fatigue domain. You see, high cycle fatigue has quite a big problem regarding experimental time needed to have a full characterization of a material. You need to do a lot of experimental tests. Basically, for each SN curve, you need about 19 specimens if you want to be scrupulous and also have statistical effects accounted for. And this takes a long time to do these tests. Specifically, high cycle fatigue that has lives of millions of cycles, you need about 2 weeks to a month of having a testing machine doing these tests. It's completely blocked for that material and that specific geometry. So in the Fatigue for Light project that we have in our group, we've worked together with Eurecat and with ArcelorMittal to design a testing strategy which significantly lowers the experimental time needed to do fatigue testing, fatigue experimental characterization. And they have developed at Eurecat a rapid fatigue test, which is based on stiffness evolution. What does this consist in? Well, they apply blocks of cyclic loading of 6,000 cycles specifically, either at a ratio of 0, 1 or at a ratio of -1 with a specific loading frequency depending on the material. And what they are doing is that after each of these loading blocks, they are doing a loading and unloading of that specific specimen at 15% of the ultimate tensile strength. And this is done to detect what is the change in stiffness inside the material. And you can see here, for instance, that the loading history for this type of test is progressively higher, okay, the stress amplitude which is applied on the specimen. And as you finish a block and then you check this change in the stiffness, you can see here that the displacement measurement varies after each load. So basically, if you are quantifying what is this change in the displacement measurement, and you plot it against the stress amplitude, you can detect here what is the fatigue limit of this specific material. And for us, it was interesting when they developed these experimental techniques to see if our model, if our formulation with high cycle fatigue was capable of giving accurate results for this type of test also. And we began to do a calibration. It's specific for a TWIP steel. And we basically began, as you begin when you do a numerical simulation, calibrating the static parameters from the engineering stress strain curve. You can see here experimental curve, and it's very good adjustment with the numerical curve that we've obtained when we calibrated our model parameters. Then we also calibrated our fatigue parameters for the -1 and for the 0, 1 curves. And then we proceeded to evaluate if we obtain the same behavior after doing this rapid loading history with the blocks of cyclic load. Sorry. In the experimental analysis, they were able to detect an increasing level of structural damage. What I mean with this is they computed a specific damage parameter based on the evolution of the stiffness. This is somehow to be understood as a macro structural damage. Okay, it's not similar to the integration point damage that you would see in a constitutive law. And we wanted to see if at structural level of the sample we were able to obtain the same behavior. And what we've seen is that we've gotten quite a good agreement in between the numerical and the experimental part. I have to say that here we only analyze the damage or the change in stiffness up after a specific level of damage, which is 0.5. Actually, here there is a typo, because this is what was able to be detected by them through the open eye, let's say, and experimentally, I mean. And you can see here what is the adjustment in between the numerical and the experimental curve. And we've also had the opportunity here to test a cycle jump algorithm, which we have developed quite some years ago also, that helped us significantly reduce the computational time of high cycle fatigue simulation. Why? Because when you do this simulation, applying the load 100,000 of cycles, cycle by cycle, you are going to be spending a lot of time with this, basically about 24 hours. And we wanted to see, okay, what happens when we use cycle jump strategies? How are we able to reduce the computational time? And you can see here, for instance, with cyclic jump or jump step, let's say, of 100 cycles, we are managing to lower the computational time until 10 hours. And this analysis can be further pushed down, let's say, in terms of computational time. Now, another issue that, or another important value that they could determine from the experiments was what is the fatigue limit for this specific TWIP material. And what they saw experimentally was that the fatigue limit was for them 260 megapascals. And what we saw in the numerical simulation was that the fatigue limit, as I'm saying, structural level, measured structural level, was 258 megapascals inside the numerical simulation, which is, again, a fairly good agreement. If you are interested in knowing more details about this specific experimental technique, which reduces the time, as I say, from testing for minimum of 2 weeks until 15 hours of testing only, you can take a look at the paper which was published by our colleagues at Eurecat. And if you're more interested in our numerical model and how this adjusts to this experimental behavior, you can attend or follow Luis Antonio Gonçalves, who is our PhD candidate working on this topic specifically. He will present his work regarding this topic in the Congress on Numerical Methods in Engineering in Gran Canaria in September. Okay, now let's go to ultra-low cycle fatigue. Okay, I'm running out of time. I have so many things to talk to you about, so I'm going to go very fast. This is a model which was proposed in 2015, and I don't want to get into details because we formulated it then and we haven't used it for the past years because we didn't have research projects that were specifically focused on this, okay? Just take into account that it uses kinematic plastic hardening coupled with isotropic plastic hardening. We have a specific constitutive law developed for that, and you can find the expressions which are based on the fracture energy inside these papers that I will put here. Just to say that this work was developed during my PhD with the supervision of Professor Xavier Martinez, Sergio Oyer, and Alex Barbu. Okay, now results regarding this. We used it for a project in oil and gas for piping industry. And here you can see, for instance, an elbow which was subjected to cyclic loading with some internal pressure. And you can see the adjustment between the numerical and the experimental behavior, which was quite good. However, we saw that regarding the failure mode, there was a slight difference because of the level of internal pressure. And this motivated us to do a whole analysis of how the failure mode changed with the level of internal pressure. You can see more results in the publications that I mentioned. I don't want to insist more here because I have a lot of news on other things. Okay, now just bear in mind that this ultra-low cycle fatigue formulation, this specific constitutive law, is perfectly capable of capturing a random cyclic loading, okay, and the effect that it has once you repeat it for a specific number of cycles, even with these very crazy hysteresis loops, okay? Now, low cycle fatigue. Low cycle fatigue, this gray area in between the plasticity and the damage domains. There is a big question that you have to answer when you're speaking about this area. And this is if you're using a plastic damage model, which you should be using for low cycle fatigue, how much energy should you devote to plasticity and how much energy should you devote for damage? Now, during my PhD thesis, I proposed something over here, but this was still quite a green approach. There was still, it could be quite developed. And we've worked a lot in this past year and a half to develop strong coupling between plasticity and damage throughout plastic damage model. What do I mean with strong coupling? Why is it needed? You see, when you have a plastic damage model which is exhibiting weak coupling, what you have is a basic plasticity model and you compute the damage variable based on the level of plastic strain, okay, that you have in your model. And this is very good. It's very useful for a specific range of application. But what happens when you are interested in migrating, for instance, from low cycle fatigue to high cycle fatigue? You had some plasticity at the beginning, but then you are going towards a load history which only needs to give damage behavior inside your model. Well, if you're using a weakly coupled model, you won't be able to do this because if you stop plasticity, automatically this stops damage. So this is why we needed strong coupling, why we needed to integrate damage and plasticity at the same time, and we needed models which would be easily reduced at each one of the base phenomena, either reduced to plasticity, either reduced to damage if needed. In this sense, we've been working a lot on 3 different models. The initial one that we tested in 1996 was proposed by Viviana Lucioni. What was proposed in 1996, we didn't test it because we were very young at that specific point. But we've started to implement this and we've tested this model and we've seen some limitations. And this is why we decided to follow some other avenues. For instance, we investigated the associative plastic damage model proposed by Wu and Professor Cervera in 2016. And we've also proposed and formulated a brand new plastic damage model, very nice and interesting idea, which is a rule of mixture based plastic damage model proposed by Sergio Jimenez. Okay, now, if you are looking at these 3 different plastic damage models, I've arranged them a bit different and you will understand very soon why. Basically, because I want to show to you there is a transition in between a less coupled behavior to a more coupled behavior. What do I mean with less coupled behavior? For instance, the rule of mixture based plastic damage model can allow 2 different surfaces, one for plasticity and one for damage, which vary, which behave in a completely different way. The implicit plastic damage model by Viviana allows 2 different surfaces, but if they are moving in a 2 different way, you're losing convergence, you have instability in this model. This is a big limitation for this model. Now, the associative plastic damage model proposed by Wu and Cervera only has one yield surface, which is common for plastic damage for both plasticity and damage together. Okay, Now, let's look at some simple evolution curves in between the three different models. What I want to say here is, for instance, for the rule of mixture-based damage model, the internal variables of the model are damage and normalized plastic dissipation, which is this kappa p variable. Normalized plastic dissipation means plastic dissipation is in a specific load increment, or the accumulated plastic load dissipation until that specific load increment, divided by the total level of fracture energy. So when you have a level of plastic dissipation which is normalized unto 0.2, you dissipated 20% of the fracture energy available for the material. When you are at a level of 1 for kappa p, you dissipated completely all the energy available. For instance, the implicit plastic damage model of Viviana had a normalized damage dissipation and a normalized plastic dissipation. These were the internal variables of the model. And for the associated plastic damage model, we have a sole unique dissipation, which quantifies both damage and plasticity dissipation together inside this specific value. Okay, if you want to know more about this, Sergio and Alejandro, Sergio Jimenez and Alejandro Cornejo, they have been working intensively on this. Specifically, please pay attention to Sergio's PhD defense, because he will have so many interesting cases to show, and he will be able to devote more time to speaking about this. Also, follow him at his talk in Oslo in Norway, where he will explain about this rule of mixtures plastic damage model. Also, follow Alejandro's talk in Oslo, because he will speak about the associative plastic dissipation model. And you can have more information about the specific equations that are behind each one of these models in a paper that we hope to publish very shortly in the Computer Methods in Applied Mechanics and Engineering journal. Okay, I'm going to go very fast. The associative plastic damage model. We have a compliance matrix over here. As I said, the dissipation variable is unique, normalized plastic damage dissipation. And this is based on a Xi parameter, which varies between 0 and 1, as proposed by Professor Wu and Cervera. 0, fully plastic behavior, 1, only damage stiffness degradation. We've applied this model, for instance, for a 3-point bending case, and we studied the crack mouth opening displacement with the reaction force, and you can see here the adjustment that we obtained. It was interesting, it was a good behavior. Then we go to the rule of mixture-based plastic damage model. I have to say this is a model that I'm deeply in love with, because the rule of mixture is something that has been used in the composite world since the 1960s. It's a very old idea, but it has never been used for describing the behavior of a homogeneous material. Because what we are doing here is we are assuming that in a specific volume of a homogeneous material, as I'm saying, we have a volumetric part which will behave according to plasticity laws, and we have the remaining, the complementary volume part, which will behave according to damage. And this is very, very interesting and very clever, because it allows you to play with these participations and understanding the behavior of the homogeneous materials, not as a combination of materials, which was done for composites where you had fiber and matrix, but as a combination of constitutive laws, of constitutive behaviors. And the interesting thing here, as I said, complementary and volumetric participation for the damage and plasticity, is that this volumetric participation is not fixed. It's evolutive throughout the nonlinear process. So if you have a material which starts to exhibit plasticity at the beginning of the nonlinear processes, but later on migrates into a damage behavior, or a combination of these two, this model is perfectly capable of capturing this. This is a very, very important characteristic. So when we are dealing with progressive redistribution of the volumetric participation as a function of this damage internal variable, we have proposed different transition functions available: linear, exponential, and potential. And here you can see the variation of the damage and plasticity participation. Take into account that damage is Kv is this damage participation, and Kp is this plasticity participation. And you can see how they can vary throughout a specific numerical simulation. You can choose in between these different laws. Just an example for linear softening laws: when you combine damage and plasticity and you use a linear transition between damage and plasticity. I don't want to insist here. Another test that we made, which is a typical test, Carlson and Gerson for plastic damage models. And you can see here the behavior under tensile and under compressive. Also important to know, these models admit different behavior under tensile behavior, and different curves, hardening, softening, whatever you need in the compression behavior. Okay. Now, when we compare, for instance, the three-point bending for the associative plastic damage model with the rule of mixture-based damage model, both of them have their particularities, and one of them can adjust better to a specific case compared to the other. Let's say that you have a lot of tools that you can use when you want to simulate a specific case here. Another case that we did, which was compressive behavior, again, a comparison between the associative plastic and rule of mixtures. I don't want to insist here again. But let's just say that we also need some transition cases, because as I said, it's important for us to be able to migrate from monotonic with fatigue, fatigue monotonic, or combinations of cyclic loading. This is why we need transitions from plasticity to damage, damage to plasticity, and we need specific transition functioning between these models just to make sure that we don't recuperate, we don't go back on the level of plastic strain, it's fixed, and we don't go back on the level of damage once we switch from a process to the other. And here, for instance, you can see what's an interesting case, for instance, when you apply this type of loading and you begin with a completely plastic behavior, then you begin to have, you pass into transition zone where you have plasticity accumulated with damage, and you continue up to a point where you begin to exhibit exclusively damage, okay? This is perfectly possible with this model. And another combination where we have cyclic loading, 10,000 cycles applied, and after that we break the sample monotonically. And during these cycles, we do this unloading here, where you can see how the behavior changes from plasticity with damage, and in the end, we only exhibit damage behavior in the part where softening is obviously exhibited. Okay, future work. What about the manufacturing processes? Well, Alejandro Cornejo has been working a lot on this, on developing specific models inside Kratos regarding metal forming, because this is an important process that we need to take into account when addressing fatigue behavior. You can see here different cases for stamping simulation, etc. Then about thermal fatigue, this is also a topic where we are very interested in. This is why we coupled the solver, the mechanical solver, with the thermal solver, and we done some simulation, very preliminary, where you apply a heat flux, for instance, on this lower control arm on this edge, and you look at the evolution of the temperature, and you look at the evolution of the von Mises stresses as this heat flux increases. And here you can see, for instance, the deformed shape of this suspension arm, a bit exaggerated, of course, when you continue applying this load. Okay, short comment on composites, okay? I'm finishing. Now, on composites, we've been also working, but to be honest, this is such a wide topic that we could probably devote 1 or 2 seminars just to speak specifically about fatigue in composites. Just to let you know what we've been doing inside this area. We've dedicated effort to coupling the high cycle fatigue formulation with the serial parallel rule of mixtures, which was developed also in our group back in 2008, I would say. Also, we've been dedicating effort at deriving reliable fatigue data from experimental tests. You'd think this is such a simple issue, but it's not, because it's very difficult to have SN curves, for instance, for the high cycle fatigue domain. For the fiber, for the matrix, in order to do a good composition, in order to isolate well what is the cyclic behavior of each component, so that you have a good control of what is the cyclic behavior of each of the composite. This is very, very complicated to do, and Barbara, our PhD student, has been working on this, on how to collect this data. Also, delamination, it's a very important phenomena for composite materials, and Ali has been dedicating the effort into formulating a delamination model for composite materials. If you are interested in these topics and you want to pursue and find out more news from us on our developments, please pay attention to Barbara's talk inside the Congress on Numerical Methods in Engineering in September also. Barbara has been collaborating with scientists from the Research Institute of Sweden, from RISE, on the behavior of fatigue behavior of carbon fiber reinforced polymer, numerical versus experimental. Also, Ali's talk, which will be focused on numerical investigation of fatigue-like behavior in glare structures, a damage assessment approach. He will present also at the conference in Gran Canaria. And please, as I say, if you're interested, please assist at their talks. Okay, nothing more from my side. Thank you very much for your attention. And I'm open to questions if you have them.
Thank you very much, Lucia. Very nice presentation. You perfectly fit the time. Thank you again for that. I think that we have at least 5 minutes or more to discuss or to comment on the presentation of Lucia. Is there anybody interested in asking? Yeah. One curiosity. When you talked about the different regimes of ultra low cycle fatigue, low cycle fatigue, and high cycle fatigue, um, can you remember? I mean, maybe you already said that, but I now don't remember it. How do you distinguish? I mean, which is the range between those different types of cycling fatigues?
Yeah, basically the difference is when you look at the experimental behavior or what you see in a typical cyclic test, let's say, when you are dealing with high cycle fatigue, you will have failures that are due to having applied a load which induces elastic deformation. So you will not observe on your specimen any plastic deformation, okay, any permanent change in the shape. However, if you continue to apply this cyclic loading, you will obtain brittle failure, complete failure of the specimen after a determined number of cycles. This is what's considered high cycle fatigue. When you go on, well, the easiest to identify, I would say, other type of fatigue in the ultra low cycle regime is when you have very high level of plastic deformation induced inside your material due to the cyclic loading, and you fracture the specimen, you completely break the sample after maybe dozens of cycles or hundreds of cycles. In between these two areas, you normally have you observe experimentally, I would say, a combination in between change in stiffness, because as you continue to apply the cyclic loading, there's a variation over there in the slope of loading and unloading. So this will signal to you that you have damage. And also you will observe that you have changes in the deformed shape of the specimen. You have permanent deformation, plastic deformations, which belong to a plasticity behavior.
Okay, thank you very much. That's a very good explanation. Yeah, I understood perfectly. Fernando, you had a question. You can unmute you.
Okay, thank you. Thank you, Lucia, for your great presentation. Very, very interesting. I have a question on the first part regarding the calibration. If I understood well, you have some points from the experimental tests, and then you mentioned that you have a calibration procedure to fit this smooth curves, right? But yeah. I observed that you have there's some scatter in the experimental data, and if I understood well, you also mentioned that you have some statistical effects, as you call them, if I understood well, and you also said that in general, when you are characterizing some material, a number of specimens are required, right? So yeah. I guess you will have some scatter in the experimental results. My question is, how do you deal with that scatter? Because not only for calibrating your curves, but also when applying your models, because the models are deterministic. But reality, yeah. Let's say reality is not deterministic. You have some, do you consider that some way? Do you have something like a confidence interval? Is there a way to account for this real, let's say, non-deterministic behavior?
Yeah, there are several ways actually to incorporate inside the modeling approach the statistical effects. As you say, when we receive these experimental results, we always observe scatter. So there are always some statistical effects over there. When we are doing the basic calibration for our high cycle fatigue deterministic model, we are averaging with the fit routine inside MATLAB a correct approximation, let's say, of those experimental points. But we can also do, for instance, weighted calibration, and this is something that I didn't mention. For instance, when we receive the experimental points, we have some points which belong to the low cycle fatigue regime and some points which belong to the high cycle fatigue regime with higher fatigue lives, let's say. And sometimes it's not that easy to find a curve that correctly approximates the entire fatigue regime from low to high. But for instance, if we know that we are calibrating for a high cycle fatigue domain, then we can give more weight to the points in the with millions of cycles in the lower part, let's say, of the curve. And we can decide to better approximate that area, as that would be the area where we will focus our numerical simulations. And the other way around, when we have low cycle fatigue and we want to do calibration for low cycle fatigue, we give more weight to the parts on the upper part of the curve, and we dedicate more effort to approximate correctly that part, because the simulations that we will do will be in that area. Now, we are approximating with this fit routine in MATLAB just that specific SN curve for that specific stress ratio that we obtain experimentally. But for instance, we can have probabilistic SN curves, which are later on treated, I would say, with different probabilistic models. This is not something that we have done in our group, but we are collaborating with research groups who are doing, where they are deriving this type of probabilistic SN curves. And then once they do this probabilistic analysis, they can give to us what is the curve that they want us to approximate. And we input inside our deterministic model that those experimental points which take into account that probabilistic effect. This is one way in which we can account for this, but also another way is, as you say, using these tolerance bands, I would say, which give you, let's say, a 5% probability of occurrence, a 95% probability of occurrence. So you have like a superior and an inferior band, and you can decide if you want to do the simulation with this specific level of reliability, 5% or 95%, and you calibrate those specific curves, you know, and when you run the numerical simulation, you input the material parameters for that specific reliability curve of 95%. This is our approach.
Okay, thank you. I guess the common or conventional or easy way of going to when probabilistic is with Monte Carlo, something I would say are approaches, but in this case, I guess that computational time is also an issue, so you have to do something like this simplifications. Okay, thank you.
Thank you, Fernando.
Thank you, Fernando. Is there any other short question? If there are no more comments or questions, then let's close the session here. Thank you again, Lucia, for the nice presentation. And thank you all for attending today. And I hope to see you all in next week in the next session of the seminar course. Bye-bye.
Thank you, everybody. Bye-bye.